1 is 4, that is a square. Again, 8 into 3 is 24, plus 1, 25 is a perfect square. 8 into 1 plus 1 is 9, which is again a perfect square. 122 into 1 plus 1 is 121, which is a perfect square. 120 into 3 plus 1 is 361, which is again a perfect square. And 120 into 8 plus 1 is again a perfect square, that is 961. So now the question revolves around the fact how many D1 quadruples are there, or in how many ways can we extend the set, or what other sets we can have as a D1 quadruple, quintuple, or so on. Okay, so this form of quadruple was later generalized by Euler, who found the following infinite family of quadruples with property D1. So the set Euler defined was, given two integers a and b such that ab plus 1 is r square, we can extend the set of two integers further by adding a plus b plus 2r, where r is this term, and further 4r into r plus a into r plus b. This will always yield a quadruple, a Diophantine quadruple with n equals to 1. This can be checked by you guys. I'm leaving it. In fact, a stronger result is known. It is known that any D1 triple can be extended to a D1 quadruple. That is, not only a D1 pair, but a D1 triple can be extended to a D1 quadruple. So this fact signifies that there must be other infinite families of quadruples with property D1. Because this just uses the fact that the first two, A and B, satisfy the condition. So it would be an interesting exercise to trying to find other infinite families of quadruples for A and B with certain conditions. Now, Baker and Davenport showed in 1969 that this Fermat set of 1, 3, and 8 was the only extension to a D1 quadruple. Given these three integers 1, 3, and 8, Fermat set was the only extension to a D1 quadruple. Which further from this we can say that it cannot be extended to a D1 quintuple, because if there was some D1 quintuple, this set shall be extended in at least two different ways. So this step of Baker and Davenport was the first step towards the ancient conjecture, which states that there are no D1 quintuples. This conjecture is too old, but the proof of this conjecture was not available to us until recently, like in 2018. At the end of 2018, we could get a proof of this conjecture that there are no D1 quintuples. In 2004, Diophantine proved using similar methods that there is no sextuple with property D1, and there are only finitely many D1 quintuples. So Diophantine is the person who works on this problem, who has extensively worked on this problem. Most results on this problem are by Diophantine. You can also visit his website. In the last, I'll also mention his website as a reference, where you can find everything about this problem. Okay, so after Diophantine, it was a paper in 2018 by Hay, Tuple, and Ziegler, who showed that there are no D1 quintuples, and finally settling the long old conjecture. Okay, so after looking at these Diophantine tuples, Diophantine tuples with n equals to 1, we'll look at Diophantine tuples for a general n. Okay, so in general, there do exist Diophantine quintuples. For n equals to 256, the example that Diophant is considered, we have two Diophantine quintuples. One is 133, 105, 320, and 18,240. The other is 5, 21, 64, 285, and 6,720. So these are the two Diophantine quintuples that we have for n equals to 256. So it's clear that what we concluded for n equals to 1 cannot be vaguely transformed for other n's. Also, we don't know an example of Diophantine sextuples, though no Diophantine septuples are known. So after trying to find Diophantine septuples and getting no results, it was natural to study the largest size of tuples with property Dn. So the first basic observation that we can do in this direction is that we can say that at least there exists no infinite Diophantine n tuples for any n not equal to 0. For this observation, we need consider any set S which satisfies property Dn, then let X equals to Ai. So any Ai which belongs to S which satisfies property Dn will satisfy the equation of the curve y square equals to a1x plus n into a2x plus n plus a3x. I'm really sorry for this mistake. These three are in multiplication. So y square equals to a1x plus n multiplied by a2x plus n multiplied by a3x plus n. For all I greater than equals to 4, ai must satisfy this equation. And the celebrated theorem of Siegel states that the number of integral points on this type of a curve are finite. Though the bound given by Siegel depends on n, a1, a2, and a3. So we need a more general bound that is free from a1, n, a2, and a3. Okay, so one other observation in this direction, let Mn denote the supremum of the size of this set with property Dn. So we can observe that for Mn greater than Mn is less than equals to 3 for n congruent to 2 mod 4. If we take n as 2 mod 4, then ai and aj cannot be congruent modulo 4. The reason being that ai and aj would be a square, and we know all squares would be a square mod 4, and we know all squares mod 4 are 0 or 1. So we cannot get 0 and 1 mod 4 finally. So ai and aj cannot belong to the same congruence class. So this will imply Mn has to be less than or equal to 3. So for the cases where n is congruent to 2 mod 4, we have got a really smaller bound, that is Mn has to be less than equals to 3. Moving on, further, for general n, Lugela proved that Mn is less than or equal to constant times log n. And this was done by estimating the three sets. Let S denote the set with property Dn, so we'll partition the set S into three sets, An, Bn, and Sn. The first An will consist of the set S intersection from n cubed to infinity. Bn will be S intersection n square to n cubed, and Cn is S intersection 1 to n square. The basic idea to partition the set in this way is after a certain point, we actually do not get any n that will belong to this set. For small n, we can handle this problem by hand. So as you must be knowing that we generally consider it for sufficiently large n. So for this case, we are taking it in order of n, n square, and n cube. So Lugela proved that An has to be less than or equals to 21. So after a certain point, that is when it will cross n cube, at max you can find 21 numbers which can satisfy this property Dn. Dn is less than or equals to a log n plus 2.152. And what is important here to estimate is Cn, and it's by trying to prove certain results in this, it has been observed that Cn is the term that gives the most. So estimating Cn in the best way possible is what we really want. So the most significant contribution comes from Cn, and that is obtained by using the Gallagher-Sieve inequality. Okay, so next we'll look at the Gallagher-Sieve again. Okay, so any doubts still here?
Could you please go to the previous slide? I want to
Yeah.
look at it once. No, it's still the same page, just different animation.
This is the one you want to see, right?
Yes, yes.
Okay.
Okay, thank you. You can.
Is this clear to everyone? If AI and AJ would belong to the same congruent class modulo 4, then AI AJ will belong to some square congruent classes, and the square congruent classes mod 4 is only 0 and 1. So if AI AJ is 0 or 1 mod 4 and given n is 2 mod 4, the resultant cannot be 0 or 1 mod 4. It will be 2 or 3 mod 4, which are not squares. So that's the problem here, and that's why mn has to be less than equal to 3. Okay, so any other doubt? Any other doubt from the yesterday's presentation as well, you can ask. Okay, in that case, we'll move on. We'll revise the theorem that we saw yesterday. Let P be a finite set of natural numbers and let T be a set of prime powers. And let X be the maximum of the set B, and the upper bound that we have of P mod T is UT. Provided that the denominator is greater than 0, we have upper bound on the size of P, that is, size of P is less than equal to summation T belong to T lambda of t minus log x over summation t belong to t lambda of t over ut minus log x. Okay, so we'll try to use this theorem to estimate Cn. I'll again like to show Cn. Cn is the supremum is of the size of the set of S intersection 1 to n square. Okay. So here I'll introduce the capital O notation. So the capital O fx is said to be equal to capital O of gx if and only if there exists a constant c such that fx is less than or equal to c times gx. And further, to use the Gallagher C, we'll need some bounds that I'll not derive here. I'm really sorry for that, but these bounds for the people who have known the flavor of analytic number theory will know that the first bound can be derived using the partial summation technique. The second bound can also be derived from partial summation, and the question why root p plus 4 would be answered a little shortly while we are looking at log p over root p plus 4. Okay, so the two bounds that we need would be summation p less than equals to x log p is equal to x plus capital O of x over log x whole square, and summation p less than equals to x log p over root p plus 4 is greater than equal to 2 times root x plus capital O of log mod n to the power half plus capital O of root x plus log x whole square. Capital N here signifies the Tn tuple that we are looking at. Okay, moving on. So let S be the set of elements of Diophantine M tuples between M and N, between 1 and n square, and we are naming n square as capital N just for our easiness, and let P be a set of primes less than x. Now, using our Gallagher's sieve inequality, we have size of S is less than or equal to summation P belong to P log P minus log N over summation P belong to P log P over UP minus log N. Okay, so I'll switch to the slide where we had the Gallagher sieve theorem. So in the numerator, we have this one being called function, which we defined as log p if t log p if t is a power of some prime, and in all other cases it is 0. For the sake of our question or problem of Diophantine M tuples, we are considering the set P as the set of natural numbers, or rather we can say the set of a Diophantine M tuple in which we are only considering the elements that lie between 1 and n square. So lambda of t is log p for the cases where t is a power of prime, and here we have considered the set T to be the set of primes. So clearly summation of T belong to T, lambda of T is nothing but summation of P belong to P log P. And for the denominator, similarly this would be log P, and for the denominator of this, we'll have to use the property of double Dirichlet sums, which many of you may not be knowing, so I'll skip it here. We'll just use this that, okay, so here I've just said it to be UP. We'll later say this UP to be less than or equal to root P plus 4, and the proof I would not say. So using the result on double Dirichlet character sums, we know UP is less than equals to root P plus 4. This uses some results of Vinogradov and many others. So the main result is based on Vinogradov, and there are many results of Vinogradov on this double Dirichlet character sums, and this is the best one that he has written. This is using the best one that he has written. Okay, so this also has a story. The best bound that he has written was in Russian, and for something like ticket, people did not know that we really had a better bound available. It was Dujela who brought our attention to that result and helped us making this bound better. Okay, so now putting in the known bounds in equation 1, the equation that we have derived in the previous slide, and using x to be log p whole squared. X is in P we have considered the primes less than x. So we are now generally we give this x some value that is related to n, because we want to keep our number of variables less, and why we don't want to keep it n itself is the reason because we want to tackle with less number of primes so that our bounds become better. So here we are considering x to be log p whole squared, or rather we can write it as log n whole squared. Okay, so putting the known bounds that we had seen in this slide, that log summation p less than equals to x, log p is less than equals to x plus capital O of x over log x whole square, and the second one, that summation p less than equals to x log p over up, and up is bounded by root p plus 4 is greater than equal to 2 root x plus capital O of log root n plus capital O of root x over log x whole square. The people who are interested in more details, the proof of these bounds and stuff can I think mail the organizing people, and then I can share with you the related papers, and you can look at the proofs and all. I just did not include them because the calculations were a little more intimidating. So putting this, we'll get size of S is less than equal to x plus capital O of x over log x whole squared minus log n over 2 root x capital O of log root n plus capital O of root x over log x whole squared. Now, as we know, capital N is n square. Putting this and making a few changes and kneading it a bit, we'll get that the size of S is less than equals to 2 times of log mod n this capital O of log mod n over log mod n whole square. Okay, so Dujela has already given a bound on this. This was a paper of Becker and Murthy who made this bound better, and this bound was made better by adding some conditions on this double Dirichlet character sums by Becker and Murthy. Okay, so now hence we have the following theorem that the size of Cn was the set that we had considered as S. So Cn is less than equals to 2 log mod n plus capital O of log mod n over log n whole square. So this Cn will help us improve the bound of S. S is the size of S, the original S, that is the Diophantine M tuple, is the sum of all these three sets. On An, we have a neat bound of 21. On Bn, we have a bound of order of log mod n, and then a constant. And for Cn, we have again received a bound of order of log mod n plus some capital O of a smaller function, which we can not look at for a few minutes. So this would say that the size of S is order of log n. By order, I mean the capital O notation. That is, fx is said to be of order gx if there exists a constant c such that fx is less than equal to c times of gx. Okay, so this will give us that the size of S is of the order log n. Okay, so this finishes the first half part of our presentation. So again, if anyone has any doubts, can ask. After this, we'll move to a generalization of a Diophantine M tuples. There are a lot of generalizations. We'll consider one of them and talk about it. Okay,
Here, can the n be negative?
Actually, yes. Because our n is for the case of this Diophantine M tuple, which can be negative, this such that aij plus 1 or n is a square. Wait, definition. Yeah. So this aij plus n has to be a perfect square. That is the only condition for a Diophantine M tuple with property Tn. So n can be negative. Now you may ask, why have I considered set of natural numbers? The reason being, you can't consider the same set in negative. So it would just be the 2 times of the bound that we have achieved. And that would not change the order to a much extent. So we just consider the problem in 2 parts. You can consider that first we have taken S as the set of positive Diophantine M tuples, and then the same set for negative Diophantine M tuples. Does this answer your question?
Yes.
Okay, thank you. Any other doubt? Okay, in that case, we'll move on. Okay, so thank you for commenting that. In this case of generalized Diophantine M tuples, we will actually not consider the case for negative. And the case of negative is the one that we have not worked on. I mean, the people have not worked on. Though it would be the same as what it is for the positive case. It is suspected so. But no one has given an explicit proof or written down something in that direction. Okay, so now we'll consider a generalized Diophantine M tuple. This is one particular generalization. I'll name other few at the end. This is just one of them. Okay, so first we consider a D1, though the first that we found was D56, a tuple with property D256. But what made people more what made people more excited was the D1 tuples, because one looks like a very small number and easy to deal with. Still, the conjecture took, you can see like how many years, until 2018 it was unsolved. Then, generalizing that, people wanted to consider a little more hard problem of considering tuples with property Dn. And now further, we want to change the square that we've had, that aij plus n is a square, to having some kth power. Okay, so now formally defining it, natural extending the above concept, we define generalized Diophantine M tuple as, given a natural number k, we say a set of natural numbers S, a1, a2, a3 up to am, is said to satisfy the property dkn if aij plus n is a kth power for all 1 less than equals to I less than j less than m. Here we are not allowing I equals to j. If we allow I equals to j, we say something as strong Diophantine M tuples. So in that case, ai square plus n has to be a perfect square, aj square plus n has to be perfect square, and such numbers are rare. Okay, so we had defined the sum of an plus bn plus cn as the supremum of the size of the set. Here we'll define mk of n as the supremum of the size of the set satisfying property dkn. Okay, so now observe any element of the set S satisfying property Dn will satisfy the following equation of curve. The last curve that I mentioned was the equation of an elliptic curve, and this is what is known as super elliptic curve. It is y to the power k is equals to a1 plus n into a2 plus n into a3. Sorry, I missed an x here. Sorry for all the mistakes. I have done a lot of them. Okay, so y to the power k is a1x plus n, a2x plus n into a3x plus n. So if the size of the set S is greater than 3, we'll have the solution of this curve. Okay, so now using a celebrated theorem of faultings, the one that was also mentioned in the last talk, that there are only finitely many integral points on a super elliptic curve. In the last talk that he mentioned was that the curve with genus greater than or equal to 2 has finitely many integral points, and the super elliptic curve is one of the cases. Okay, so this theorem of faultings is the theorem following the one of Ziegler, which was that y cube equals to a1x plus a2x plus a3x. Sorry, y cube equals to a1x plus n into a2x plus n into a3x plus n has finitely many integral points. So this theorem of faulting says it for arbitrary k. Okay. So recently, Anup Dikshit, C. Young Kim, and M. Ramamurthy proved some bounds on this set S with property dkn using Gallagher's sieve. I'm not mentioning it here because I'm not proving it here because it uses something called as Roth's theorem and many others. Okay, so the concluding remarks on this theorem. So the Gallagher sieve is one of the most basic of the sieve techniques. Like earlier, long years back, we had Brun sieve. First one was the Brun sieve, then Selberg sieve. Brun sieve was the one that was used to resolve the Brun's theorem that I stated yesterday, that the reciprocals of the twin primes converges. And that was the first remarkable result of sieve theory. And that was using the Brun sieve. Then Selberg sieve was used to look at the primes. And then we had the sieve of Linnet, that is the large sieve. But all of them have a lot of calculations and really look intimidating for the person who will first see them. So Gallagher's sieve looks like a stepping stone to sieve theory and is one of the most basic of the sieve techniques. So for the most basic of the sieve techniques would be interchanging summations and partial summation, but they are considered as the basic techniques. So removing them, so the technique specifically of sieve theory would be the Gallagher sieve, the most basic of the techniques of sieve theory would be Gallagher sieve. But this is the one that needs a lot of information to be used. And that information should be useful. It should not be some vague information like we used yesterday. What we used was really so vague and crude bounds that we cannot even satisfy the condition of the Gallagher sieve. So in practical sense, it is really hard to find problems where Gallagher sieve can be used because we really need a large amount of information in hand to use Gallagher sieve effectively. But for this case of Diophantine M tuples, it looks like the Gallagher sieve provides the best available bounds. Like people have tried to use Bruhn sieve, Selberg sieve, large sieve because we can use large sieve because if you remember, I mentioned yesterday that large sieve looks at B mod T and Gallagher sieve or the larger sieve looks at B mod T where T can be any prime power, while in large sieve they can only be prime powers. So we really are using just the prime, not even prime powers. In the proof we have only used the primes, but still Gallagher sieve provides us the best available bounds. Okay, so this is it for this problem. Now I'll like to mention the other generalizations of these Diophantine M tuples. One of them can be rational Diophantine tuples. So what we had looked at was integer Diophantine tuples. That was integer Diophantine tuples that AI, A1, A2, A1, A2, AM were positive integers. Not positive integers, just integers. Sorry, this is for M. Are positive integers. Are integers. While we can also consider AI, A2 up to AM as rationals, and those are said to be rational Diophantine tuples. Then similarly, we have generalized rational Diophantine M tuples. The generalized Diophantine M tuples for are the kth powers. For the rational Diophantine tuples, we have stronger results. We have every pair, every triple, every quadruple can be extended to a quintuple. So our conjecture or the result, like existence of no quadruples, fails in the case of rationals. So for rationals, we also know a few of sextuples, and we have found a sextuple from which we can generate infinitely many sextuples. Though the search for septuples is still not complete, we don't know any rational Diophantine septuples. Then we have strong Diophantine triples. This I've already stated. So for this, we only have triples. That is AI, AJ plus N. Here I can be equal to J. Here I less than equals to J will hold, and these are termed as strong Diophantine M tuples. So for those who, okay, so any doubts up till here or any point that I've said a little hastily and you want me to repeat it? Okay, so in that case, I'll just give you a further reading. So for further reading, you can look at this reference of Tugela's page, this on Diophantine M tuples. Like Tugela is this one person who has most of his papers on this topic. You can say that all his career he has been doing just Diophantine M tuples, just variations of these Diophantine M tuples. And now it looks like the problem has finally been almost resolved. There are a few ifs and buts left, but there is no long-standing problem that is left. For integer Diophantine tuples, for rational Diophantine M tuples, the things are still a lot to be looked at. Okay, so this is the page where Tugela has provided all information about this problem. Anyone interested can look at it. Okay, so for this is it from my side. If in case of any doubts, you can please ask.
Thank you, Rishidari. That was a wonderful talk. It's now time for the questions. There's a question in the chat by Shami Malhotra.
Okay.
Is there any motivation behind these Diophantine M tuples?
Okay, so these are these ancient problems in number theory that we see a pattern and then we try to see, and that pattern start fantasizing us, and then we try to find more of such patterns, and that's it. That's it. There is no strong motivation, I would say, but yeah, these special numbers have some relation. So these Diophantine M tuples have been studied in terms of these Fibonacci numbers, and it has been proved that the Diophantine quadruple cannot exist out of a Fibonacci number or so. So yeah, so there is no real motivation in terms of like trying to prove some real life application problem or something. But yeah, it is just like playing with numbers. So I hope it answers your question.
If anyone else has any question, please kindly write them in the chat box, or you can unmute yourself and ask now.
For those who are interested or know the paragraph conjecture, know a little bit of graph theory and are interested in paragraph conjecture, if we suppose the paragraph conjecture, we have better bounds on these Diophantine M tuples, both for the cases of square and for the kth degree. Yeah.
If there are no questions, I think we can end today's talk now.
Yeah, sure. I hope I've given you some insight into Sieve theory and this problem of Diophantine M tuples. Okay, so that's it. Thank you for listening to it. I hope you enjoy doing maths and also enjoy all other things. So yeah, thank you.
Once again, thank you.